Hey everybody, Dr. Retzik here with you. This is our second video in 7b. Here we are trying to make the transition from the complex spectral theorem to what's called the real spectral theorem. So what you want to think about in terms of the real spectral theorem versus the complex spectral theorem is something like this. So let's think about this big box that has all the operators on V in it. Now, some of those are normal. So maybe this box is the ones of these that are normal. And we know that when V is finite dimensional and the scalar field is the complex numbers, that box, the normal ones, is precisely the operators that have orthonormal bases of eigenvectors, the ones that are diagonalizable with respect to some orthonormal basis. Okay, the real spectral theorem is an example where in order for things to work out over the reals, you need to be a little more special. The complexes, they give you some wiggle room because everything factors and there's a number whose square comes out to -1. It's just easier and cleaner over the complex field. So what it's going to turn out to be is if you want the same conclusions for an operator, that there's an orthonormal basis of eigenvectors, all right, it's not going to be enough to be merely normal. Among the normal operators, some of them are genuinely self-adjoint. And for inner product spaces over the real scalar field, self-adjoint is what's going to characterize those operators that have orthonormal bases of eigenvectors. Now, this is a slightly longer discussion, and we need a couple of preliminary results. The first one is this lemma here. So this lemma is just a means to an end. And the lemma says, if T is a linear operator on V, so V is a finite dimensional inner product space, but that's all we know about it. And B and C are real numbers with B squared less than 4C. Seems like kind of out of nowhere. That's a weird condition. Then this operator, so T done twice in a row plus B times T plus C times identity is invertible. Okay. This definitely seems a little out of nowhere. Let's prove this and then see its utility towards our discussion of the real spectral theorem. Okay, so here's the proof. Just take any V not equal to 0 in V. So I suppose this proof doesn't work if there is no such vector. But let's assume there's a non-zero vector in V. Otherwise, V is the most boring inner product space there is, the one with just the zero vector in it. Okay, So start with any non-zero vector. Then the inner product of t squared plus bt plus ci acting on v with v. All right, let's multiply this out. So what do we got here? We got t squared v against v plus b tv against v plus c v against v. And all that is just additivity and homogeneity in the first slot. Okay. Now, hey, I think we need an extra hypothesis here. This t needs to be self-adjoint in this lemma. And the reason I just realized that was I want to write this like this. Which is legit if t is self-adjoint, but if t isn't self-adjoint, then that's totally false. Okay, but now that we have the right hypotheses in there, here's what we're down to. V with v is just norm v squared. Okay, and now this is bigger than or equal to, by Cauchy-Schwarz, good old Cauchy-Schwarz. Okay, this first term, well, that's norm tv squared. Now this middle term, the size of it, at most, the size of that is absolute b norm tv norm v by Cauchy-Schwarz. So that line is at least as big as if we took away as much as we possibly could. So Cauchy-Schwarz is in here. And then we still just have that last term. And now the beauty of this is just algebra. This is like the move you do when you complete the square to argue for quadratic formula. You can just trust algebraically, this is this. It's norm TV, take away absolute b over 2 times norm v, all squared, plus c minus b squared over 4 times norm v squared. And that you can see by hypothesis is positive because you got something squared plus something positive. So this is greater than 0. Okay, so what? Well, here's the upshot. Therefore, this vector here, in the first slot of the original inner product, that can't possibly be 0. Because if it were 0, that inner product would have come out to 0. So, t squared plus bt plus ci acting on v is non-zero. Thus, t squared plus bt plus c is 1 to 1, because we just argued its null space is just the 0 vector. Any non-zero vector is not sent to 0 by that operator. And since the inner product space is finite dimensional, always in chapter 7, the inner product spaces are finite dimensional. 1 to 1 is equivalent to invertible. Okay. So this is a technical little thing that just says, hey, certain combinations of the operator t are guaranteed to be invertible. Now, you wouldn't think necessarily that this lemma is worthwhile or important unless you had been attempting to prove the main prize of the day, which is the following theorem. If T, a linear operator on V, is self-adjoint, then T has an eigenvalue. Okay, first of all, in 306, you already knew this was true without the hypothesis about T being self-adjoint in the situation that the vector space was over the scalar field C. So every operator on a finite dimensional complex vector space, doesn't even have to be an inner product space, we know has an eigenvalue. That was the first thing in chapter 5 in 306. And it really stemmed from the fundamental theorem of algebra, which says over the complex field, things will factor. Okay, so what's noteworthy about this theorem is now we've taken off the hypothesis that V has to be over the scalar field C, but we've added the hypothesis that T is self-adjoint. Okay, so self-adjoint operators have eigenvalues. That's the upshot of this theorem, and the proof will look familiar. Proof. Okay, so here's the situation. You got a finite dimensional inner product space V, so let's say this is a dimension V is n, just for specificity, and then you got an operator T. T takes inputs from V and produces outputs in V. And all you know about this operator is that it's self-adjoint. And now we're trying to claim that it definitely has an eigenvalue. Okay, here's the route. Take some vector V besides the zero vector. If there isn't one, then all of this is a silly discussion because V would have only the zero vector in it, and that's boring. So we're going to assume V is a non-trivial inner product space. Okay, now make a list of vectors in V. Remember, it's V on both sides, so little v is there, but also you could do t to little v and you would end up over here, and t squared to little v and you would still be in here, all the way through t done n times, where n is this dimension, to little v. Now look at this list. It's got n plus 1 vectors on it in an n-dimensional vector space. Therefore, the list can't be linearly independent. In other words, some combination of the vectors on that list comes out 0. So a0 v plus a1 tv plus ... all the way through an t to the n v equals 0 for some coefficients a0 through an not all 0. So there's some non-trivial combination of those n plus 1 vectors that comes out to the 0 vector. Okay. Thus, 0 equals a0 plus a1t plus ... an t to the n, all acting on v. Okay. Now you're going to be asked to believe something here in your reading from chapter 4. In the RETSEC 306s this year, we did chapter 4 in one day. In your 306, you might have spent more time or less time. Chapter 4 was about polynomial factorization. And the key thing here is that stuff in the parentheses, that polynomial in the letter capital T definitely factors in this way. There's some constant out in front, and then you get some irreducible quadratic pieces. So pieces of the form, and here's where the lemma comes in. T squared b1t plus c1i dot 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 all the way through t squared plus b, I don't know, k t plus cky times, so this is still times t minus lambda 1i times dot 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 all the way through t minus lambda m I. The point is, every polynomial, even over just the reals, every polynomial factors into a bunch of irreducible quadratic pieces and a bunch of linear pieces. So that parenthetical term acting on V is really splittable into all these different operators, one right after the other, acting on V. Now, to say that these pieces are irreducible is to say precisely that bi squared is less than 4ci. So by the lemma, each of those is invertible. So let's be crystal clear here. In purple, each one of these is invertible, which means it can't take something non-zero and have the result be 0. Now this C is non-zero. That's just some number sitting out in front. If it were 0, that would say the polynomial is identically 0. That makes no sense. Polynomials have maxes and mins and they're curvy. All right, so C is non-zero. And none of those purple guys can take something non-zero and make it 0, which means one of these must take something non-zero, namely this, and produce 0. In other words, one of lambda 1 through lambda m must be an eigenvalue. So I'm just going to cut to the chase and say, by lemma, one of lambda 1 through lambda m must be an eigenvalue. And that's it. We did not have access to this back in 306 in chapter 5, where we did the exact same moves and we made this list here, because we didn't have access to the idea of the adjoint and the idea of an operator being self-adjoint. But if you add that hypothesis that T is self-adjoint, then whether V is over the complex field or the real field, you are guaranteed to have an eigenvalue. Okay, and that's good for us moving forward, because now once you have an eigenvalue, well, at the very least, you can start a basis off and have the first column of your matrix be some number and then all zeros. So we're on our way once we believe that self-adjoint operators have an eigenvalue. Okay, it's going to take some time for us to build up to the full statement of the real spectral theorem, but we're making strides. Okay, see you next time.